Started, so everyone grab yourself a sandwich or a wrap, get yourself some chips, and go ahead and get started here. Welcome to the user group, Go Utah user group. We're happy to have you all here today. Just a quick note to those who are your first time. Boxes above you with green lights are microphones. They're designed to pick up questions that you might ask the presenter, but that means that they are very sensitive. So if you whisper, we'll pick that up as well. If you want to end up famous on YouTube, go ahead and have whispered conversations. Otherwise, try and keep the chatter to a minimum during the talk. If you want to speak, we have lots of openings for speaking. It's beginning of the year, so there's lots of opportunities. We want to foster community here, and so if this is something you've never done before, but you might be interested, if you are intimidated about giving a really big talk and maybe want to give a smaller talk, like come talk to me, come talk to Carson, talk to Mariah. We'll help you get it figured out, try it out. We just want to hear from everybody in the community. This is more about building a tech community than it is about presenting like the most technical talk you've ever heard. Although we do have some really great speakers. Jobs and hiring. I know a lot of people, this is a weird market. If you're looking for that, if you want to find people, if you want to get a job, Slack is the best place to network around that. There's lots of great stuff that happens there, not just jobs and hiring. So come hang out with us, even if you're not interested in that. But that's sort of like the offline social space for all of the different tech people here in Utah. And then we're going to turn the time over real quick to Ryan. He's going to talk to us about Go's type system. And I think he's probably one of the most familiar with compilers as far as presenters that I've ever seen. So it'll be really interesting to hear him talk about that. We'll go ahead and turn the time over to Ryan. Take it away.
Sweet, thanks. Let me turn this into slideshow mode. Cool. Can y'all see me? Everything good? Okay, cool. Yeah, so I'm Ryan. Oh, sorry.
Share your slides. I don't see your slides right now.
You don't see them? Okay, here, let me reshare them.
Okay, see your face, and that's great.
Okay, yes, let me here. Resume presenting. How about that? Does that work now?
There you go. Now your slides are up.
Sweet. Okay, let me, okay, cool. Now we're good?
Perfect. That looks great.
Cool. Sweet. Hi, I'm Ryan. I'm joining you all from Seattle today. I'm supposed to be in Utah, but some stuff came up, so I will not be in Utah today. So I thought I'd just give this presentation over the airwaves. I am a compiler security engineer. That means that we're kind of worried about vulnerabilities within compilers. I don't really do much Go nowadays, but I used to do a lot of Go. This talk kind of came out of some discussions that happened on the Forge Utah Slack. If you aren't on that, you should get on it. But there are some questions in the Go channel that I found. I guess it's not some of the type system stuff that I guess I hadn't really thought about too much, but some people were learning and trying to figure things out. And so I thought might as well kind of give an overview and a talk for those people who are learning Go's type system and trying to figure things out. More experienced people might not find this particularly interesting because I am just going to go over the type system, and it's really not anything that magical, but hopefully you'll learn a thing or two. So what are type systems is kind of a good place to start out with. So type systems are a syntactic method of kind of defining like what your program is going to do for the computer. It helps in laying out memory. So when you're programming, you want everything on this. You want most things on the stack, and so the compiler needs a way to figure out how much stack space to allocate, and so it will use types in order to kind of figure that out. Optimizations are really helpful. You can do a lot of optimizations with integers, but maybe with floating point numbers, you're not going to be able to do those same optimizations. Lots of times you have programs that maybe you are converting between units. So you have like, seconds and microseconds, and then you want kind of a type for both of those, and so that you're not accidentally mixing them up, and the type checker will enforce that for you. So you can kind of mess around with that. And then it obviously kind of abstracts your program, and so that you can use your program for multiple things. Generics kind of help with that, and we'll get into like what generics are and how they work in just a minute. But in general, just types also can kind of help you abstract your programs over kind of your own specific domain, whether that be your business logic or whatever else. So Go has a lot of types. So on the top, we've got kind of, I guess the first 2 lines are kind of your base, maybe what you would call your base types. So you have your any, which is just an interface that has nothing in it, which means it can be literally anything. Your string, your booleans, your unsigned integers of all types, and your integers of all types, along with just int, which can either be a 32-bit or a 64-bit int, depending on the platform. You have your float 32 and 64s, your runes, which are int 32s, which you see with string processing and UTF-8 sort of stuff. And then probably the least used type in all of Go is the complex numbers. So you have the complex 64 and 128-bit complex numbers. I don't think I've ever seen somebody use complex numbers inside of a Go program. If you have, that's pretty cool, but it's not really a thing that anyone uses. Kind of the reason for that, Rob, well, I think it was Rob Pike. I joined a Go compiler call one time. They have office hours, and they were talking about how at one point they wanted Go to be like mathematical and to kind of try to capture that space and do like a kind of Fortran type stuff, but that really never took off because oh, it wasn't Rob, but it was because Rob kind of had a really didn't want to add some more complicated math types in. So you have your channels, which are your synchronization primitives that let you send information between different Go routines. You can decide whether these channels can only send or only receive based on where you put the arrow. And you can also decide whether they're buffered or unbuffered, which are technically, your channel is technically the same type, but under the hood, the implementation changes a little bit. So you have your arrays, which are statically allocated pieces of memory that can contain n number of things of whatever you want. And then you have your slices, which are dynamically sized and have a underlying kind of array structure that gets copied over when you append, or you have your capacity, your length, and actual underlying data. You can use keyword structs to build out structures or to build out kind of your custom data types. As you say, you can put any number, you can compose, you can create fields that have, any number of these types in them. And you can kind of compose structs upon structs upon structs. You have your function types, which, take in any number of arguments and then return any number of return values, kind of in tuple form. And then you have your named types, which are different from alias types. So your name types, you're going to have something that you name, and then you're going to give like one of these other types that I have listed here. And essentially what that does is it lets you control, or you can add methods to that named type. And then it also kind of lets you do some interesting things like, the duration type, I believe, is a int64. And so you can, but it's an int64. You can't use it as an int64. It needs to be a duration, and it needs to be cast to an int explicitly if you want to use it as such. And that's to kind of stop you from trying to think of a duration as an int64, and rather kind of trying to get you to think of a duration as an actual duration. And then it also has some methods associated with it that are, duration specific. Aliases, on the other hand, are not that. Aliases let you say, maybe there's some other type that is in another package that you want to re-export. Then you can alias it, and you can kind of re-export that type through the alias. In all functions, it's kind of like a find and replace sort of deal. So it functions essentially as, macro, or like something that like it is a T. It isn't necessarily some other concept that won't type check. You have your interfaces, which are kind of a set of methods that something must cohere to or must implement in order to get type check. And then you have your constraints, which are also backed by the interface keyword, which is a kind of really odd design decision in my opinion, because it is kind of weird that in generics you can have your interface, which has the methods, but then you can also constrain things via the interface keyword. And you'll see these as you put you can say a constraint would be another type. You could say int, or it could be a struct, or it could be a channel, or whatever. And you have these ors, these little pipes, and then you can put other constraints with this tilde. And the tilde is a little special in that it lets you constrain your types to say that anything that has the underlying type of this, of this other thing. So for example, anything that's an int64, meaning that duration could also be one of those things, I will accept as as a parameter for a generic function. It's kind of odd. Just to be quite frank, I read through the spec, the type system spec while I was writing this talk, and constraints and what is considered a base type is kind of muddy. So if you're confused about it, I guess I really understand how it can be quite complicated, but kind of just generally speaking, we're talking about kind of our primitive types, our booleans, our floats, our runes, our strings, that sort of thing. And if you're wondering, well, is this thing a base type of this other thing, you probably should just go look at the spec, because it's probably a little bit easier to do that way. Also, if you guys have questions, feel free to stop me at any point. I forgot to mention that, but I have no problems stopping and explaining something. So everything at Go is passed by value. Even pointers are passed by value, and that's because a pointer is just a number. I guess that's not maybe necessarily true. I guess I don't know if Go has fat pointers or has interesting, weird things going on there, but pointers are just numbers in general. And it doesn't really have a concept of a reference, except I'm going to talk about references in the next slide. But pointers can either point to the stack or the heap. This is something that people don't quite, quite get, I guess, coming into Go, because it can be kind of weird to pass stack pointers around. You can run into some undefined behavior in other particular languages if you're passing around stack pointers, because that stack frame could be gone, or you just really don't know how the optimizer is going to handle that sort of thing. Go uses escape analysis in order to figure out whether or not, taking the reference of something, in this case A, is going to point to the stack or the heap. In this case, I would probably say that it's not going to escape to the heap, and it can just store through the stack pointer. This is also helped by the fact that Go has really interesting stacks in its Go routine. It's a stack per Go routine, and it can be really interesting kind of how the memory is laid out there. And it's a lot different than how you would expect in something like Rust or C or C++. So reference types is something that you'll hear thrown around with Go's type system. This is something that are, they're still values, but they're represented by some sort of data structure which has a pointer underneath. So, you have a string, for example. You can slice up your string if you want to. At the end of the day, you are going to have some sort of underlying pointer. And if you mess with things that have these kind of underlying pointers, then it will, it's everyone that has a copy of it is going to see it. So you see this with maps, you see this with slices, except slices are a little bit trickier. And what else do you see it with? I guess channels. If you close a channel, then everybody sees that. So there are things, that are reference types because they are, you pass them around by value, but under the hood, it's kind of opaque to you. That there are things that hold references or hold pointers to kind of what is going on under the hood. So that can be kind of tricky, and in Go you do really have to be careful about appending to a slice that has been passed in by a function. It's not going to do what you expect it to. It's never a good idea. Questioning who owns the slice is kind of a good idea, and reference types are, I think, a little bit tricky to reason about for the kind of new Go developer.
Can I ask a question?
Yeah, go ahead.
So this is an interesting correction for me, and I've been laboring those false assumptions for a long time. You're saying everything's passed by value.
Yeah, everything is passed by value.
Strings are immutable.
That's correct. Yes.
And so for a long time, I've labored under the delusion that passing a string passes a copy of the string, but you're saying it actually passes a copy of this struct,
Which has a pointer to the string.
Which has a pointer.
Small.
Correct.
Passing strings around costs you very, very, very little.
Actually, that's a great question. I might have used a really wrong example. I'm pretty sure that if strings are immutable, then I don't see why you couldn't just pass around the pointer to that string. I don't think you're copying the value unless you're reassigning it. I guess I'd have to now I'm going to have to go and figure out. I don't think that do you have to pass a?
It does. So
Is it the same to pass a string that's 10,000 characters as it is pass a string that's
yes,
0?
but it does copy the struct. So the struct itself is
Right.
not.
Yeah,
Right,
that's
The pointer, the underlying pointer is not.
Yeah, I'm pretty sure that's the case.
That was never clear. I learned just as somebody that's, again, does this for a lot, still doesn't know things apparently. But
Yeah.
Value and strings appear to just be like raw values.
I think
Right. So often.
Yeah, and I think maybe the best example of this would be a map, right? Is like if you have a map and you pass your map around, it's completely free to pass your map around. And then as you're like adding to the map, then everybody gets a copy of that has ever seen that, right? And I don't mean a copy of that. I mean that everybody who's observing that memory is really what it is, right? It's not magically copying it into everybody's, into everybody's address space. But I would be shocked if it's making copies. In something like C++, you might see that. You would see that C++ has move, which is its own can of worms. But if you don't move it, then you could be copying. I don't think that Go is that way necessarily. I'm almost positive, and I guess I should have double checked that before. But I was pretty sure. I mean, it's been like 6 or 8 months since I've touched Go. So you may be right that strings get copied, but I don't think they do.
Hopefully, that's great. I always the decision of like, should I take a byte slice or a string to me has always been a little vague.
I'm not quite sure how to get this.
Right? And I understand copying a byte slice is cheap.
Yes, it is.
Copying a string was not as cheap, but it sounds like it's about the same.
Oh, copying? Well, there's a difference between copying and passing by value. Or passing, right? Or like passing it, because I don't think that strings have. Anyways, I don't.
That's why they made them. And so
I think that's great. That's what you want. So the difference is not performance; it's that if you pass byte slice, they can munge with it.
Yeah, it
cannot munge with a string.
Yeah, it is an unsafe pointer under the hood that gets passed to the function. So okay.
But there's no way for somebody to take my string and mess with that pointer without. Right, that's private and that.
Well, I mean, accessing the string, if strings are immutable, which again, I'm sorry that I am like brain farting here. It's been a bit since I touched Go. If strings are immutable, then you can't touch that underlying unsafe pointer. You can only read from it. But if you modify, I would think that if you modify the characters of the string, then everybody sees it because you've touched the data inside of that pointer.
No, it is
I don't
still-
think that that's illegal in Go to touch that. So
I mean, I know for a fact if you pass something a string and you can chain, only make a new one.
Yeah.
Right? It only makes a new struct. It copies the string.
well, if you append it, it would. But I don't know if you modify index 0 if it does. I don't think it does.
Yeah.
Because otherwise, every index into a string would cause a copy. So I mean, strings are immutable in the sense that there's like an underlying slice to it, right? Or like an underlying pointer that like will grow as you append to it. But then I guess, you're getting into a different string at that point. You're copying things. But like you can modify the string just because it's immutable and it's something that points to some piece of memory doesn't mean you can't modify the underlying memory. Right. Okay.
Hey Carson,
Would you mind just summarizing that?
But don't worry about it. The bottom line is
No, the bottom line is that
strings around.
when you're passing strings around, don't worry about it.
go
It's
through
not going to, yeah, it's not going to
it's
hurt
something
you.
you can't change it under the hood for you.
No,
Pass
no,
around.
yeah, it's completely safe to be passing around massive 10 kilobyte strings. It's not going to hurt you. So it's not going to copy it. Unless you append to the string, then it's going to copy it. So, okay, so named types. So named types are interesting in Go because anything can be, except for an interface, I guess. Interfaces can't be named types. But name types are kind of the ability to be able to add extra kind of meaning or kind of abstraction to these kind of more basic types like strings or ints or functions, for example. So like this first one, it's an email type. And so, when you're passing strings around, you have to explicitly tell the type system that this is an email that you're passing around, which I find very helpful. You're saying this thing has, domain specific, what's it called? Domain specific use cases. And I want you to make sure that you really know what you're doing. So you do have to cast to an email. And then it can have its own methods on it, and it can have a pointing receiver, which is really helpful. The other thing that is worth a mention is that functions are first-class types, just like any other type in Go. And you can see that here. So I have a function that implements read by calling itself, and that's like completely valid, super legal Go. And I have used this many times. You actually see this in the Go standard library with serve HTTP. It's like the handler func. So a handler func implements what's it called? Like the handler interface by calling itself. And that's why you see, you have to wrap functions in like http.handler func or whatever, because it implements the http.handler interface. And under the hood, it's just calling itself. I find that really, really cute. I really like it. It's a really nice feature of Go that not many people use. You should probably reject it in code review though. It's very much a me feature. I feel like you probably it's just a really weird concept that you can do this sort of thing. That is really cool. You can also alias anything you want. So if you're like worried about passing around functions passing around functions as parameters somewhere, you could just alias it rather than doing this name type, because again, name types and aliases are very different. And in that way, you can just kind of have a nice name for your function rather than like actually typing it like this, where it becomes its own separate type that can have its own methods on it. Anyways, so Go is pretty cool that way. So zero values is something that I'd like to touch on before we get kind of into some more weeds. Every Go type has its own zero value. In other words, Go values must be initialized. The reason for this is that if you've ever done C or C++, if you just say like int x and then you put a semicolon, who knows what that is? It's whatever is in the stack at that time. If the stack hasn't been zeroed, then good luck. You have no idea what's in there. And in fact, if the compiler can prove that you never initialized that int value x, it can do some really aggressive optimizations. And it can kind of say you've invoked undefined behavior. I get to do what I want with it. Go does not have that. Go does not have that at all. Go requires that everything has a zero value, and in fact, it's kind of something that's built into the compiler at a really deep level that everything has a zero value. And Go actually, I believe in the Go book, like the Go programming language, they talk about zero values, about how important they are, and kind of the Go's philosophy is that you should make the zero value useful. That's a hot take, in my opinion, but like, I appreciate that, like the level of care that Go had for zero values tends to be pretty interesting and nice. So, your reference types, your interfaces, your slices, your channels, maps, you're gonna see that all of those things initialize to nil. So they are nil. If you attempt to access anything inside of them, then you will get null pointer dereferences. You have your base types, your int, your complex, your floats, everything. It's all zeros, with your exception of your empty string, where it's an empty string, and with a length of 0 and nothing in the buffer. And then your structs are all the fields inside of your structs are recursively initialized to their 0 values. So if you have a struct, that has a field that's a struct, that has a field that's a struct, that has a field that's a struct, then it will kind of initialize all these values for you. If you go on Compiler Explorer and you read the assembly that gets emitted when you initialize a struct, you will see that it gets zeroed out. The memory will get zeroed out, or like it will randomly start kind of, assigning things to like the empty string or whatever else it is. And yeah, anyway, these are really important. It will come, we'll come back to this in just a second. So untyped and typed nil. There's no such thing as untyped nil in Go. And this is something that like really messes with people's heads, I feel like. You think of null, a lot of times in like C or C++, you're thinking of null as like 0, or like it points, it's a memory address, right? It goes somewhere, and it's this memory address that is 0. And if you attempt to access it, then 0 typically, the operating system is, paged to throw, a seg fault. And so like when you're loading from that pointer or you're storing to that pointer, then you get a seg fault. With Go, it's not the case that nil is just 0. Nil is its own thing, and nil requires that it has a type. So you can't just say that X is nil, because what is X? Like, we don't really know what X is. X a nil interface, or is it a nil struct, or is it a nil channel, or is it, what sort of nil is it? And it's something that you have to kind of define, because nil is not this pointer to 0. It's a pointer to something, and you kind of have to know what that pointer is to. In this case, I have shown something that has bitten me many times using Go. You don't really, this is a contrived example. It's probably the easiest way to read this, but it happens a lot of times when error handling. But you can see that R is a strings reader, which happens to implement the io.reader interface. And it's initialized to nothing, and reader is a struct. So technically that would be nil. And you see, you cast it through a reader, and then you say, well, is it nil? If it's not nil, then go ahead and read from it. And this will panic. And the reason why it panics is because you would think that the nil check saves you here, but it does not. And why is that? Well, interfaces under the hood, much like strings, actually have a pointer to the underlying implementation of what they are, like what you're using. But the interface itself, like the interface type, is not nil in this case. It's actually pretty valid. It's just internally the thing that it is, it has stored that is an implementation of reader happens to be nil. And so in this case, the reader variable is not nil, but the internal reader is nil. So the reader, the nil check is fine. But when you actually call read, then you will get a null pointer exception. And this is something that has bitten many people, and is pretty nasty about kind of nil. And it's something to keep in mind when you are returning nil. What type are you returning of nil? Because if you're not careful, then you can end up, if you have some error type that you return from your function, and it's not an error, lowercase e error, you're returning the actual pointer, or you're actually returning the implementation of that thing, then it's pretty easy to accidentally cast it to an error, lowercase e error in an assignment, and suddenly error not equals nil has bitten you. It's gonna, it's not nil. Anyways, so you do have to be careful.
Sorry, I just want to plug. Brandon's too nice to plug his own stuff, but Brandon's done an entire talk on nil is not nil.
Yeah, perfect. I did not know that. That is something that you should go watch then. Everybody should go watch Brandon's Nil is Not Nil. Because nil is not nil. This is correct. So nil has to be typed. So it's a quirk of Go.
Sorry, can I ask you a question?
Yeah, go ahead.
Thank you, Carson, for plugging me. Also, so when you do that check, right? Because we do this all the time.
Yeah.
Is the right-hand side nil, right? Error does not equal nil. Is that right-hand side of the check an untyped nil? Or should you, like, does the compiler coerce it to be like a nil error interface?
That's a really, really good question. I like that question a lot, actually. So this is a great question. So it would coerce the type of nil to the thing that's on the left-hand side. So in this, or cast, or whatever you want to call it, it would be more like promote. I don't know what you want to say. But your nil on the right-hand side is going to turn into whatever type on the left-hand side, which is the reader, right, of this expression. So reader is an IO reader. So it says that the nil in this case is an IO reader. So it determines that its type is IO reader, nil. And that's why the nil check fails. I would bet, and I guess I'm not certain on this, but if you were to wrap that nil, if you make it an IO reader of nil, it might work. Yeah, I think the problem might be that the nil there. Actually, what it would be is you would say not equal to IO reader, and then you cast it to, and then internally you have a strings.reader, and you cast nil to that or something. So you have to be careful, right? It's like, even if you have an IO reader and then you put nil in there, it doesn't know what nil is. Nil isn't a type, and it does not implement reader. And so you would have to say, well, no, actually, I think it's a nil type. Like, it's a nil reader, strings.reader, that is.
Hey, Ryan.
It's annoying, yes.
So I've worked with code that we had to do that. And if you do cast that nil to whatever type reader is,
yeah,
it will check correctly.
Will it? Okay, cool. Yeah, I was gonna say, the second option that you have for this is reflection. Excuse me, I'm a little sick. Yeah, reflection is your second option for that, and no one wants to do that. So, okay. Yeah, it's just so messy. Yeah.
It can get kind of ugly though if you don't know what the underlying type being returned.
That's right. Yeah. Yep. And that's why reflection exists. Is if you don't know the underlying type of the nil, then you can just use reflection. A really weird quirk of Go. So I'll try to keep my opinions out of this. But it's just a funny little quirk. Okay, so next we have casts and assertions. So casts and assertions, there's two different things. So you have your casting, which is converting one type to another. This is something that happens statically, right? So if I cast like a duration to an int, that's something that's like very legal, right? And statically, the compiler will decide, okay, a duration to an int. It actually kind of drops that conversion at compile time because it doesn't matter. It's something that the compiler doesn't need. It's just the type system needs. So under the hood, like it doesn't, like the processor doesn't care if you're adding a duration or if you're adding an int64. They're the same thing. So that gets dropped under the hood, but that's something that casting happens statically and ahead of time, and something that you have to do for any two different types, and you have operations of with an int and a float. You have to cast your float to an int or your int to a float or whatever it is. Go is explicit in that types must match on all operations between each other. So like an int, you can have an int and a float. You can have an int and a complex number. Oh crap! I forgot to put this in the slides, but this is something that also gets really weird with constants, where constants are actually untyped. So nil is not a constant. Well, it is, but it isn't. Nil's not nil. as go watch Brandon's talk. But you know, when you have a type, when you have 1+1, it kind of depends on what the result you're using. You're using that for. So that 1+1 doesn't really mean anything until you realize that it's actually a duration that you're assigning that to, and then Go will turn those into durations for you. That's something to another kind of thing that you have to watch out for, is the fact that the types of constants will get resolved after the fact, unless you up front. Well, I don't know if you can even say up. I think you can say up front, like this is a float. But if you don't, then it's untyped. So assertions, though, are a little different. Assertions can be determined statically, but not all the time. And if they can't be determined statically, then it turns into a runtime check. It happens to be very cheap, so you don't really have to worry too much about it. But it's telling that the compiler, yeah, this thing must be that thing. So it's going to fail if you attempt to assert that this is a reader. You can catch that failure. Well, catch, I say that colloquially. You just have an extra value that you assign. So you would say, like, reader, comma, okay, colon equals that expression at the top. And that would let you check to see if it actually fails or not. Otherwise, it will be a runtime error if you assert this thing and it's not that thing. And then after you assert it, then the runtime kind of knows what's going on. And so it can start using, I guess you can't use myvar after that, but you can use whatever you reassign it to after that as a reader, because we know that the runtime check has been done and the compiler is very happy to actually use those, like type check everything to a reader after that point. But under the hood, you're using that myvar variable. But yeah, anyways, just a little difference. So type, oh, I guess I did talk about, yeah, so type checking.
Hey, Ryan,
So type, yeah.
I think you have a question.
Oh yeah, go ahead.
Yeah, I was wondering why. I've always thought it was kind of odd that constants behave that way.
Yes.
Why them in particular?
Good question. I don't know, to be honest with you. I mean, you have these. It's kind of hard to tell what a constant is. For example, though, like it's pretty clear what this constant is. This, 0.1f. Like it's telling the compiler it has to be a float. I mean, the more interesting thing is that, is it a float 64 or is it a float 32? And math.abs, I believe, is on float 64s. And so you're talking about, so it's going to turn that into a float 64. I think it's kind of hard to tell what, you either have to have a default value, at which point you're casting every constant to whatever you want it to be. So for example, if you want your ints to be, or your constant ints to just be a regular int, then you're going, if you have an int 64, if it's, if you're on an operating system that has only int 32s, then you're casting every constant to int 64. That's not very portable. I guess it's extra portable. But it wouldn't be nice to figure out that you have to cast everything to int 64 all the time when you're using it as as whatever it is. And so it resolves everything at compile time, just to make your life a little bit easier. It also, the other thing too is that you have, these named types like duration, right? You don't really know, like you would want things to be kind of automatically turned into a duration. And so it gets resolved at compile time, and it kind of, you would prefer it to not have to be everything to be casted in this way. You would prefer it to just kind of automatically understand that this constant being multiplied by a duration turns into a duration, rather than having to say this constant duration times by this duration turns into a duration. So it's kind of ease of use, but it does get wonky sometimes. And I've heard like a message or something, or maybe a hand raise. Is that correct? Sorry, I can't see y'all, so that's
There are
not
little kids running around. I think occasionally their noises peek through.
okay. Okay, cool. Did that answer your question though?
Yeah, that's very helpful. Thank you.
Okay, cool. So type checking Type checking is an algorithmic process of kind of determining whether or not the types match. Type checking is really not the hard part, to be honest with you. Type checking is, does this thing purport, or does this program actually have all the types that match? Does it say what it, what you're actually trying to express here? Is it actually, is it sound? Do all the types match? It's not particularly crazy for the compiler to do this sort of thing. Abs returns a float and it takes in a float, and it knows that the type checker knows that X is a float because abs returns a float. It knows that Y is an int because I declared it so, and X plus Y is clearly going to fail when I try to do that because that plus operator needs to have two of the same type on either side. It's not particularly crazy. With Go does have any, which means that it could be anything, and that if you want to use any as an int, then you need to tell the Go compiler that, hey, I'm going to assert that this thing is an int. Casting any to an int does not work well because you don't know whether or not it's actually an int. It's not something that the compiler can determine ahead of time statically, so you have to kind of cast it. Turning something into any also kind of, if I remember my Go correctly, boxes the type, meaning that it allocates. So it boxes the type, so it allocates, which means that, yeah, you really do have to assert it under the hood. And for underspecified types like any, or maybe it's an interface that also has other methods that you don't know about, that has to happen at runtime. You see that in something like read from, like the interface read from. So you have a reader, you can also do read from. So sometimes this interface specialization is what that's called. But type checking is really kind of not the complicated, not the really interesting thing that goes on. It's just like check to see is everything the same thing. So
I would say it's one of my favorite things. It may not be like the most complicated to implement, but it's like one of the most useful things.
It is.
Functions with 20 parameters, whatever. Like
for sure.
Great.
Yeah, it's awesome. We do like we really do like type checkers. They're pretty nice. And Go's type system is really not that complicated. So it's pretty easy to type check. It's really straightforward. One really interesting thing about Go is it uses what's called structural typing in a lot of places. So you see structural typing in interfaces where you say that this thing, right, this reader has a structure to it. It has a read method actually, and it takes in a buffer. You have, and then it returns an int and an error at the same time. In a tuple. And it's kind of nice to have this kind of structural typing. Some people may call it duck typing. I think that there are other connotations to that, though. So structural typing is kind of more what I would call it, just because that's all I know. But yeah, so you could say this thing has this structure, and then Go will kind of run with that. And that's something that you don't see in something like Java, where Java is not structurally typed. I wish I could say what the opposite of structural typing is. But anyway, you would have to say, I have to extend this interface. This is something that, I tie myself to the dependency, rather than saying this is kind of the structure of the thing that I'm going to be taking in. So interfaces are kind of the most famous example of that for Go. The other things that is also structurally typed, though, are structs. So structs are structurally typed. You do have to cast them in between each other, and there are restrictions. But essentially, if it has all the same fields and all the same orders and all of the same struct tags, then it is the same type. So if you have some struct A and struct B, it turns out that you can just cast this, or sorry, cast. You can cast this A to a B, which is cute. I think you can use that in APIs sometimes, which is really helpful. Like when you have, your database layer, and then you have like a, what's it called? You have like an API layer, and it just so happens that they line up just perfectly. Then you don't have to like do any weird data manipulation there. You could just kind of cast them over. Obviously, it causes a compiler error if either of these don't match at any point. But it is kind of nice that Go is structurally typed in this way that you can kind of say like it has this sort of thing. We want these sort of fields in this sort of layout with these names, and kind of Go just takes care of that for you. And it's statically typed at the same time, which is really helpful. Okay, so kind of the last little section of this is generics. So I've given a talk on generics before, but we're going to kind of go over it again. The Go team prefers parametric polymorphism, is what they call it, which is like really, what's it called? I guess ivory towery speaking. But essentially, the idea is that polymorphism lets you use some like single value like edit for many different types, and then your parametric polymorphism is you let somebody pass in a type as a parameter. And so I have these two, you have a vector type or a vec type that under the hood, has an element type of any. So these little square brackets are saying, we have some type E that you will pass into me, or I will infer. And then it can be anything, meaning that I can take an int, I can take a float, I can take whatever, it doesn't matter to me. And the compiler will take care of this when it's time to. And then same with sorting. If something, if all of our elements are comparable, then it means that we can sort them. That's actually not true. I'm now realizing that comparable means that you can compare equals and not equals, but that doesn't mean that they're necessarily ordered, meaning there's no like ordering to those types. So you can have your types that you pass in, and you can constrain them with different things, and we'll talk about that kind of next slide. So type constraints are the things that you use to constrain generic types or constrain your generic methods to kind of say like, I am going to do some things that maybe I'm summing a list, and summing a list requires, it could be anything that has the plus operator defined for it. So that could be a float or an int of any type, even complex numbers as well. We can take just about whatever. And so you can, write this summing method, sum of a list, and say that, essentially anything that has a plus in it, you can use, and it will just kind of take care of that for you. It's really helpful, but it does have some really interesting limitations in that you can't really do that for structs, for example. You couldn't say, oh, I have an I have anything of this kind of struct type. It needs to be able to be taken in. That's not something that you can do. It's something that they're working on. But there are some kind of interesting things when it comes to this sort of thing. I want to kind of impart upon you that type constraints are not unions. I know that's maybe a little, I don't think that's a hot take, but people really like to use them as unions, and people like to use generics as unions. If you look at the Golang channel in the Forge Slack group, you'll see that people use them as unions, and that's fine. A lot of Go code you'll see in the wild, you will see used as unions. The issue is that they're not quite unions. You do have to end up casting them, casting your generic defined parameter. And like, for example, in the case of data, you would have to cast data to an any and then type assert on it. So you're saying it can actually be anything, and then you're putting runtime checks in. So that's kind of like a poor man's union types. I don't know if I would really, I don't think generics were built for that. And if you look at kind of Go compiler discussions, you'll see that not too many people in the compiler team really like that idea. They'll tell you how to do it, but it's not like they exactly endorse generics for that, and you probably won't ever see anything in the standard library that does stuff like that. I think there's only one built-in constraint, which is comparable, and comparable I'll talk about in the next slide or so, because it's a special case of type constraint. And constraint, your constraints. What was that? Constraints cannot be used in typing an assignment or parameter. Why did I write that? What's that about? Oh, I see. So you can't like do something, you can't say like var x is, you know, an A in this case, because it's a constraint because of these little ors that you have here, your little pipe operator. It wouldn't let you assign something as an A because you don't really know. It's a constraint, right? You don't really know what type it is actually. It's not a union, and so obviously you can't use A as a type that you assign to. You could use it as a parameter so long as it's constrained here and it's named like E or something, but you couldn't, you know, take in an A. That won't work very well unless you're actually using generics. And then, you know, these ors are things. It could be a B or a C or an underlying type of int, and then all in all, it also needs to be a reader. So it could be an underlying, you know, it could be a B or a C or an int, but at the end of the day, it also needs to be a reader. And this little tilde, I think I mentioned at the beginning, but it tells the compiler that anything with the underlying type of T may be used as that thing. So if you have type A as an int, and then you use tilde int, the constraint will resolve to int, but it will allow you to pass things in that are of type A. This is again because you have things like the duration type, and you want to be able to use them when you're just operating on integers. It also makes for a really interesting, instead of having to copy lists over lots of times, you can actually just use generics and constraints to operate on those lists. And so, like for example, with sort, you could put tilde int, and you could operate on anything that could be an int, like a duration. If you were not to do that, and you had an array of duration and an array of int, you'd actually have to copy those ints over into that int array, which is a really weird. I mean, it makes sense, but because we don't know, what's underlying that array, and you'd have to, type assert on that sort of thing. But that would essentially be a type assertion on the list. That's I don't think something you could do. So, anyways, generics kind of allow you to do that sort of thing. So constraints are weird. So comparable is its own thing, and it has its own type checking rules actually, which is that so if something is comparable, if you were to have an interface of M, let's say, some method, interfaces happen to be comparable, but if you have an interface of M, not only does the interface, like the pointer type itself is comparable, right? But it also must implement M. And so you can have, I thought I had an example here, but I don't think so. If you have comparable here, you can actually omit this or M here, because interface M is comparable, and it's only comparable if you have two interface M's, if that makes sense. So you're only allowed to compare interfaces of the exact same type, but you don't actually need to specify that an interface has a particular method in it. It will automatically kind of generate this comparable or M thing for you. So like you can notice, actually, yeah, I did have it here. So you can notice that f of A is valid. F of G is also valid. I ran this through the Go thing, so don't worry, it does compile. And then another quirk is that if you have this type right here, you have this tilde string and tilde byte. It means that anything whose underlying type is a string and anything whose underlying type is a byte, it gets turned into this thing called a byte string. So I think I mentioned at the beginning of the talk, but things are it's complicated, I guess. Like what a underlying type is versus this would be called a core type. It's kind of a mess because this is a special case essentially that you can use string or bytes for just about whatever you want. Yeah, it's kind of weird. String is a comparable type, but the underlying bytes of the string are not because it's a slice. So if you have this string or byte, it just so happens that you can actually use it as comparable, which is funky. It's weird, but it helps a lot when you're dealing with things that are kind of string-like or byte-like. Just really quickly, an aside, I guess I'm realizing that I'm taking a while, but so why we can't have zero types or union types? Because constraints aren't unions. It's zero values, it turns out. So generally union types are kind of a response to the zero value in a language. So like, for example, in Rust, you can't just initialize something. It has to be, or you can't just like declare something. It needs to be initialized to some default value. Then Go, it's the zero value, which is zeros. So like if we were to add unions to Go, and we just declare R to be a result of int, and maybe it could either return an int or my error, what would it be? And the answer is you don't really know. If it's nil, then like why are we making it nil at that point? Excuse me, that just seems very odd. The compiler guys don't like this. They don't really know what to do about it. And it may be the case that we will never have union types in Go because of the fact of how deeply built in a zero value is to the Go programming language and kind of to the type system. Anyway, that's just an aside. So type inference, kind of our last little couple slides. So type checking, I kept saying it was easy because that is the easy part of the type system. Type inference is the hard part. So x : 1 will get turned into a float. That might be wrong actually. 1.0, because it's 1.0, it is a float, whereas just saying 0 would turn into an int. Your constants are untyped, and things don't get typed until compile time. Things kind of get resolved. But that's where inference comes in, where you have to actually infer the type rather than kind of you telling what's going on. And generics have this form of type inference. So if you have like max, for example, it is a built-in, but it is technically defined as a generic method. And the generic T needs to be ordered so that you can actually compare less than or equal to or whatever, or less than. And so Go can actually determine that Y is an int, and so max is actually getting initialized with some ints. Type inference is really, really, really slow in general. It's like a known very, very hard problem in programming language design. And Go really, really cares about compile times. Many of you may have noticed your Go builds have slowed down by like 10+%, because just by upgrading to Go 1.18. And that's because generics make it so that type resolution becomes a lot harder, and like the type inference becomes harder. The example on the right here, we have a shape interface that has an area, and oops, I guess I forgot to finish the append. But the idea kind of hopefully should get to you. But the fact that we are appending a oh man, I really messed this example up. If you were to append a circle, append a square, because you have a T of it doesn't know what, and so it would expect that it's a circle, expect that it's a square, and it can't figure out that actually both a circle and a square are a shape, and so we should allow the calls to append because it's a circle and a square, which are both shapes. That's something that Go will likely never have because it's really complicated, and it gets turned into a really hard problem if you allow for that sort of thing to happen. And kind of like the last little part of this, just to nerd out for compiler people. So Boolean satisfiability is a known NP-hard problem for specific types of Boolean formulas. And it turns out that if you do not restrict type inference at all, and you just let, you write the type inference algorithm like the correct way, like just fully letting it infer everything, it turns into this, this Boolean satisfiability problem. So I stole this from Merovius. He's a Go compiler developer, but you can see he has this Boolean formula here: X or Z, Y or not X or Z, and Y or Z, and Y or X or not Y. And in order to decide if something like S is a valid constraint for a type, the Go compiler would have to solve this, figure out for which, you know, X, Y, and Z, what true or false values actually correspond to that formula for it to all be true. That turns out to be, you know, you have to try every possible combination, which is an NP-hard problem, and we have solvers to do that sort of thing. And Go just refuses to take that compile time, which is understandable. That's why you'll see in Rust, for example, compile times are very, very long. It's because it will actually solve this formula. This is something that the Rust compiler would like just, yeah, wouldn't have. Excuse me, wouldn't have a problem with. So yeah, hopefully one day we'll have a little bit better inference, but it's not something that you can expect. So anyway, that's all I got. Any questions or thoughts, comments, concerns?
If you're confused by the generic stuff, don't worry, you probably don't need it. You can go for a long time without generic.
Don't use generics. No, yeah.
Not a
Generics? Yeah, generics are really, really weird. I guess I have opinions on those generics. I'm not a really huge fan of it. Not in the sense that like I do want generics. I do think that their implementation is, unless you are the standard library authors, we have a very specific use case for it that you think is a really good idea, then generics are just not it. And using type constraints, again, that's another thing that they built out for their specific use cases in the standard library. It's not something that you should really be thinking too hard about, probably, when you're writing your gRPC services. So, yeah, it's yeah. Excuse me, I'm gonna have to get a drink of water.
interfaces do, like, you can do so much with interfaces that you don't need.
That first bus function.
Yeah, so the only nice thing about generics is that under the hood, when it gets compiled, a lot of the times the generic type goes away. So meaning that the method gets like copy and pasted for the type. Whereas when you're interfacing something out, like for a while it used to be that when you sorted something, you were sorting based on an interface of less, right? The issue with that is that you're allocating for a full interface, right? Versus if it's just like an int32 that you're sorting, you don't need that extra space.
Okay. Yeah, that makes sense.
So yeah, but just generally speaking, use interfaces.